Hello, everyone. Welcome to pay attention to our work about incremental transformer structure enhanced image inpainting with masking positional encoding. Although image inpainting has achieved significant advances in recent years, they still suffer from some dilemmas. Firstly, limited receptive fields. Learning semantically consistent textures is difficult for traditional CNNs. Secondly, missing holistic structures. Recovering key edges and lines for scenes, especially ones with weak texture, is difficult as shown in the figure. Thirdly, heavy computations. Training GANs with large image sizes is still very tricky and costly. Besides, no positional information in masked regions. The inpainting model tends to repeat meaningless artifacts in large irregular masked regions without explicit positional clues. These motivate our work of incrementally inferring the holistic structural information and positional information to boost the performance of the inpainting model. Specifically, we leverage a transformer-based model to tackle holistic structures. Further, we propose a novel incrementally training strategy with zero initialized residual addition to incorporate the structural information into a pre-trained inpainting model. Furthermore, we introduce the positional encoding for the mask region, which improves the performance of image restoration. Our model pipeline is shown here, which is composed of TSR, SSU, SFE and FTR, and we will detail each component within it. In order to overcome the quadratic complexity of the standard self-attention, our TSR consists of vanilla attention module and axial attention module. Besides, to improve the spatial relation, we also provide relative position encoding for each axial attention module, which improves the structure recovery results. To capture holistic structures for high-resolution images, we should upsample the generated edges and lines to target resolution. However, resizing causes zigzag as shown figure F2I. Because there are ambiguities in the canny edge from different image sizes as shown in figure B and C, we can't use edge to supervise our upsample network. Since lines got from a wireframe parser have good discrete representations without any ambiguities as shown in figure D and E. If the model is trained in lines, it can also achieve smooth high-resolution edge maps as shown in figure K. As for our Fourier CNN texture restoration network, it is mainly consist of several FFC block. Our structure feature encoder are used to encode structure into feature maps, then multiplied by related zero initialized parameters, alpha, and added to the FTR. Finally, we design a positional encoding for masked region. We utilize a 3x3 kernel to extract the distance and direction information relative to unmasked region. And we encode them into positional encoding, which can improve the results of high-resolution inpainting. We use L1 loss, adversarial loss, gradient penalty and HRF loss to optimize our network. The proposed ZITS is trained on two datasets, Places 2 and our custom indoor dataset, which can all be tested in both 256 and 512 resolutions. Besides, we also test the inpainting ability on high-resolution Matterport 3D in 1024. Here are the qualitative inpainting results. Compared with other methods, our ZITS can obtain clearer borderlines. Furthermore, ZITS achieves prominent improvements in the structure recovery compared with Llama. Besides, we utilize PSNR, SSIM, FID, and LPIPS to assess the performance of all compared methods on the Indoor and Places 2 datasets. Our ZITS can achieve the best results on all metrics across several resolutions. Our TSR can also achieve much better results on both Indoor and Places 2 compared with MST. It demonstrates that the transformer-based TSR is amenable to learning holistic structures in a sparse tensor space, which can benefit the results of ZITS a lot. We also provide several ablation studies of our components. MPE and GC can slightly improve the performance. Besides, if adding structural information without zero RA, the improvement is limited. The line charts of PSNR and FID during the fine-tuning shows zero RA enjoys better convergence and stability. We further exploit the effects of MPE in high-resolution inpainting. From the right figure, ZITS with MPE generates images with natural and smooth colors. Finally, we further provide several high-resolution image inpainting results. All in all, we propose an incrementally structure-enhanced inpainting model called ZITS. We use a transformer-based structure restorer to get much better structures. A novel zero-RA strategy is leveraged to incorporate structures into a pre-trained inpainting model with a few steps. Besides, the proposed MPE can further improve the inpainting performance. And ZITS can achieve state-of-the-art performance.